Welcome back to ECE 320A. Not a week from today, but a week from Thursday is our third exam. Exam number 3 is on the 12th of April. And prior to that, you'll have 2 more homework assignments that are due. Homework 7, which is mostly convolution, is due Thursday. And homework number 8, I'm not sure what that's going to include, but it will be due Tuesday. A week from today is when that's due. What I want to do for our objectives or goals for today's class is first get your vote on when you might like to have a review session. And I guess you could vote by saying no review required if that's appropriate. But that will be your in-class participation. You'll want to make sure and write those days and hours down that will work for your schedule and turn that in. If none of those work, you can turn in and say none work for me, but with your name you'll at least get credit for participating. That's what I'm looking for on that. Then we will go through some transfer function discussion, deriving H of S's, our transfer functions for passive and active circuits. And that will get us, I hope, up and running, and it will be helpful for your last homework problem that's due on Thursday, I believe. I hope that discussion will help you in that regard. We will then talk about system responses and the S-plane diagram, or where the poles live in your S-plane and how that relates to the system response. That discussion will transition us into finding sinusoidal steady state response if you're given a transfer function. Meaning you don't have to necessarily find the complete response in order to determine the sinusoidal steady state response. And what I want you to take away from today's class is if you have a circuit, which let's say this table represents a circuit, and now you shake it at a given frequency, if that table was linear and time invariant and you're shaking it at a particular frequency, what do you know about the transfer functions that might be associated with that system or circuit? If you measured currents or voltages, what kind of a response after the transients have decayed, that's the steady state, you're going to see a sinusoidal response if it's a linear time invariant, and the frequency with which it will be responding is consistent with the input's frequency. So you shouldn't be expecting anything weird to be happening if you have a linear time invariant system. If you shake it at omega naught, your outputs, wherever those are or whatever those are, should be at the same frequency omega naught. What may be different is the amplitude of that sinusoidal response and its time relationship or phase difference between your input excitation and what you're measuring at the output. We will then, given time, talk about or look at determining this H of j omega, which is the frequency response. That's walking along the imaginary axis under the circus tent, is one thing we've been talking about this entire semester. Let's look at how we can find that graphically or compute that information graphically. You may want to quickly do it analytically or with your calculator. That's okay, but I think it's insightful or helpful to see what can be done or how this H of j omega can be interpreted if we look at it from a graphical perspective, from the S-plane diagram. As promised, the first thing that I want you to do is actually put your name on a piece of paper to get credit for being here. And on that piece of paper, I want you to vote for the time slots. Now, it may be that they go a little bit longer than an hour, but if you have to be somewhere else, I'm just sort of blocking this out. Theoretically, we'll have 3 possible time slots on Monday. the 9th of April. Tuesday, a week from today, we will have 2 possible time slots. The room is already in use from 4 to 5. That's why I'm starting at 5 on Tuesday. And finally, we have the same 3 time slots on the Wednesday. And what I will do is if you vote for several, I will just keep track of which of these times gets the most votes, and I'll try to then accommodate that with respect to when we hold the review session for exam number 3. You can vote for more than one time, but don't vote more than once for any one time. I'll just count your vote once. So don't stuff the ballot box for any one particular time. I know this is a Tuesday and they're voting maybe elsewhere, but this is our election today, is which of these candidates, time and day, is going to win. And you have as many as 8 votes that you can cast, actually 9 if you say you're counting not available for one of the votes. Is that clear? Do you have that? Just make sure that gets handed in before you leave today, and that will be an in-class participation problem. Let's now talk about transfer functions of circuits, and we'll quickly go through the first piece of this because we've already seen it in many different ways or forms. I want you to start getting comfortable with a system being represented by a transfer function that you can now just plop in a box, and you have this block diagram description. That will get you ready for 340 because that's the class that you'll take next, is signals and systems. You need to know how to model signals and how to find system descriptions, and in this case in particular in the form of a transfer function. In 340 you might see those as, and here you do too, differential equations. You might put them in a state space representation. There's all sorts of ways of modeling your system. In this discussion we are treating it as a transfer function, capital H of S. It's coming from a linear time invariant circuit, which means that it's now simply a ratio of polynomials in S. As we have discussed, we can now find the output response in the frequency domain, which I'm trying to be consistent and use capital letters, or in the time domain with lowercase. In the frequency domain, if we jump into the frequency domain, then we can find this output by simply multiplying the transfer function times the Laplace transform of the input waveform. And you should be able to find capital X of S if I give you a decaying exponential, or if I give you a exponentially damped sine or cosine or some combination thereof, or if I give you an impulse, if I give you a step, if I give you a ramp. You should know how to find the capital X of S for that, and then multiply that by the system's transfer function, capital H of S, to obtain the system response. Meaning you have a signal transform, capital X of S, you have a systems transform, and their combination gives you a signal out. So you have a signal going through a system giving you a signal out. If you worked in the time domain, then we have that convolution operation, which is that star between little h of t and little x of t. Little x of t now can be any generic waveform that you want to apply to your system. What is little h of t called? That's your impulse response. That's the inverse Laplace transform of your transfer function, capital H of S. You now can convolve that impulse response with your input waveform in the time domain to generate your output response, y of t. If you found capital Y of S, then you simply have to inverse Laplace transform to obtain lowercase y of t. Let's now look at some circuits. Here is a passive. By passive, we just have R's, L's, and C's. We don't have to energize those elements to make them work or for those to function. This particular circuit we have talked about a lot, so I'm not going to spend time drawing it. Hopefully you kind of know, oh, low-pass filter, RC low-pass filter, boom. This is a first order, so I'll talk a little bit while you're maybe sketching if you want. But again, these notes are available. The transfer function between the input X and the output Y in this particular circuit is found or can be found by thinking of a voltage divider. We have the impedance of the capacitor divided by the impedance of the sum of the, the sum of the impedances, R and capacitor. That's what I've indicated as H sub 1. Maybe I should have said that this is now this ratio of the output's Laplace transform to the input's Laplace transform. We will talk about different ways of writing this. They are equivalent, but in this particular case, I would refer to this representation of the transfer function as being in time constant form. The time constant here is the RC product. And that gives you a value in seconds that tells you how long it's going to take for that system to naturally respond. And if your single time constant is 1/10 of a second, then how long will it take for the transients to decay in this low-pass filter? 5 of those time constants, 5 times 0.1 is now 0.5, or in a half a second we would be in a sinusoidal steady state condition if x of t was a sinusoid. If x of t was something that had a longer tail, then the transient would last half a second, and then if the tail was a transient, it might go longer, but it's now inducing. So whenever the tail finishes, then a half a second later is when you would stop seeing anything happening in that particular circuit. That particular representation of time constant form can be contrasted with what I will call in the next line the transfer function written explicitly in pole zero form, meaning it's factored, and it's not, there aren't very many factors for whatever reason that the bottom of the R and the C were cut off, but I think you can understand what I have there. Now we have how many poles and how many zeros, finite poles and zeros. We have no finite zeros, do we? We do not have any finite values of s that cause h sub 1 of s to vanish or to become 0, and those are the numerator polynomials that we're looking at there. And the denominator polynomial, we simply have s to the 1. We have a first order low pass filter. That makes sense. We had one capacitor. We simply had a one energy storage device circuit, and that gives us our first order in this transfer function. And how we represent these, whether it's in pole zero form or time constant form, may be of importance as to what we want to do with that particular transfer function. But they're equivalent. We will use the pole zero form when we're looking at it graphically, when we're sketching these x's and o's in the s-plane. And the time constant form, we will transform our transfer functions into time constant form when we want to sketch the Bode plot. because that's the form we want. We want to have this 1 as our constant being there, and then all we have to worry about is where that pole or 0 is located, and we can get that from its time constant. Let's now look at another circuit which we haven't looked at in this class, I don't believe. It's an active circuit, and it's an inverter circuit. Now we have an active device. We have this op amp, and this is the interconnection structure, or the passive devices that are, or passive elements that are attached to this active device. Implicit in this diagram is the power supplies that energize this op amp. I haven't explicitly indicated those, but you would have to connect this op amp with the appropriate power supplies to make it work or to have it function. And that's implicit in my diagram. In this particular case, is this op amp in a, what I would say, nice configuration, or is it going to simply saturate or flip back and forth between the rails of your power supplies? And what question am I asking in that regard? Does it have negative feedback? Is it in a negative feedback configuration? That's what I'm really asking to begin this process of analyzing. Or do I have something feeding back the output to the inverting input terminal of that op amp? And indeed I do. So this particular op amp configuration is functioning in a negative feedback configuration, and that allows us now to make these assumptions that you do not have any currents going into the input terminals, and the inverting and non-inverting terminals are at the same potential, the summing point constraint. So you can say effectively that V sub P and V sub N, which I will label as the non-inverting and inverting input pins, are at the same potential. If that's the case, let's now analyze this, or find the transfer function between the input voltage V sub I and the output voltage V sub Z, or V sub 0, and KCL is a convenient way to do that. If I now label this node as V sub N, here is the V sub P that I was referring to. If I perform a KCL at the inverting input node, I see that I have current going to the left from V sub N, and I have current going up out of V sub N, and I have nothing going into the op amp by the ideal op amp assumption. And all I need to do then is find the current going to the left, which in the frequency domain is now this V sub N minus V sub I over R sub 1. Those are all functions of the complex frequency variable S. And I have the current going up, which is V sub N minus V sub O over R sub F. I'm saying R sub F for the feedback resistor. Those are my only two currents, and those need to be 0. But because I have this in a negative feedback configuration, I now know that the summing point constraint is in effect, or that V sub P is equal to V sub N. And if we look at V sub P a little more closely, we see that it's actually grounded. Consequently, we have V sub N effectively or virtually grounded. If that's the case, we can now put this to 0, and we now have just two variables in representing signals in our equation, V out and Vi. The others are constant resistor values, and we can solve those, or we now have this V sub I of S over R sub 1, and I could say that's still the minus, is equal to V sub O of S over R sub F. And if I now solve that for the output voltage, giving me my transfer function, which is this scaling or negative gain. That's my inverter behavior for that. And that could be my transfer function if I wanted to say, oh, my second circuit now has a transfer function of capital H sub 2 of S. Now, what if that one's not a very interesting circuit necessarily, so let's look at one that's maybe a little bit more interesting. And I think this is then circuit 3. Let's look at a low-pass filter that is active. And now we have just really added one more component, an energy storage device, around this op-amp. And in particular, we have connected it in the feedback path in parallel with the feedback resistor. And that interconnection structure now, even though it's not much more complicated than the inverter circuit, will actually give us a low-pass filter behavior. And you know what that looks like. It's going to be passing frequencies in the low frequency range, whatever low frequency is. That will depend on where we locate the pole or the break, and then it will roll off. And this is a first order low-pass filter. We have one energy storage device. The only difference we really need to concern ourselves with is now we could say, well, let's just call that entire combination in the feedback path the feedback impedance, Z sub F, and now we have the same analysis that we had before. Meaning if we look at this Z sub F, which is just R sub F in parallel with 1 over SC, then we have this product of those two impedances divided by their sum. And if we put both the numerator and denominator over the common denominator of SC and cancel that, we have then R sub F over S R sub FC plus 1. And that's now our impedance in the feedback path, which as an impedance, it has no zero factor and it has a pole factor. If we now wanted to find the transfer function between the input voltage V sub I and the output voltage V sub O, we simply have minus, since it's this inverter type configuration, minus the output impedance divided by the input impedance, structurally just like we derived in the inverter circuit. Here's our output impedance, Z sub F, and our input impedance was just R sub 1. And if we divide that R sub 1 into, let's say, the numerator of our Z sub F, we have R sub F over R sub 1 as a number. S R sub F C plus 1. This you can see then as first order. Here is our time constant. Let's just call it tau sub 1. Or if we wanted to, we could write that in the pole 0 form. Where is our pole located in this particular transfer function? This is now a transfer function. This is a way of creating a single-poled system with a gain. Oh, what's the DC gain of this transfer function? This is the value of that transfer function when S is equal to 0. We have minus R sub F over R sub 1 all over 0 plus 1, or it's really, because it's in time constant form, the DC gain jumps out at us. That's just the numerator's expression, with the inversion being minus. Meaning if we put in a constant input signal, as long as we don't saturate the device, our output will be in the steady state scaled by R sub F over R1 with an inversion. That's what that means, the DC gain. If we wanted to know, and what does that tell us? That actually tells us the level that we're starting at in absolute terms. If we convert it to decibels, we would have to take 20 times the log of that number, and that would be where our Bode plot began, or begins. Then it will be flat in our straight line approximations until we reach the break frequency, which is our pole. That's why we might be interested in the pole location. In this transfer function, where is our pole? It's when that factor, that denominator factor, equals 0. And that's going to occur at minus 1 over R sub Fc. And if you wanted to quickly think about what this is doing in terms of a frequency response, if you said, oh, what's this going to do in my graphic equalizer? It's going to be flat, and then it will drop down. This particular point is our break point, or our break frequency. This value, if we're sketching this in the Bode plot sense, this is now 20 times the log, and I'm going to simply do the magnitude. So this is now the magnitude of our DC gain's absolute value. So I'm not going to worry about this inversion factor. And since it's first order, we will simply be going down at 20 dB per decade, or the slope of that will be minus 20 dB per decade. And what's a decade? A factor of 10. If you wanted to know about how fast it's falling in a shorter distance of frequencies, you might start talking about octaves. And an octave is a factor of 2. A decade is a factor of 10, and an octave is a factor of 2. If we said that this 1 over RC, if our pole was at 4, and let's say that R sub F was equal to R sub 1, we would have log of 1. What's that? 0. So this would now be at 0 dB until we reached whatever I said this was. Did I say it was 4? I don't remember what I said 1 over R sub Fc was. Did I say it was 4? We'll have to replay the audio and see if I'm being truthful or not. Then at 4, in our straight line approximation, we would start coming down at 20 dB per decade. So if this was 0 at 4, then at 40, we would be down at minus 20. At 400, we would be down at minus 40. Does everybody see that? That's why we did all the algebra in K through 12. So we would know how to interpret slopes. It's just now we're doing it in terms of a dB horizontal, dB and our vertical scale, and our horizontal axis is logarithmic. All right, that's our third circuit. Let's look at one that hopefully will help you with your homework. So I'll call this circuit number 4. It's not going to be exactly like your homework, but it should get you a long way to the answer that you need if you understand what we're doing. Suppose that now I have this op-amp circuit that on the non-inverting terminal, I now have some interesting pieces connected to it. Actually, let me put my input indirectly into that particular non-inverting node. I'll call this R sub 1, and this inductor now has an impedance of SL. And I still have my output, V sub O, and let me have some negative feedback to allow this device to operate in a linear region if I don't drive it too hard. And now I have R sub 2 and R sub F associated with the inverting terminals of that op-amp circuit. Again, because we have this resistor in play, we do have negative feedback. Which allows us now to make the same kinds of claims that we've been making all along. If somebody wanted to know what this current was, I sub P, what would you tell them? That's 0. And this current here, I sub N, is 0. This point, let's call that V sub P. Let's call this V sub N. So I'm kind of squeezing things together. And I wanted to actually start expanding that naturally. I just tried to tap the screen and expand. Never mind. Now, we have negative feedback, and what we want to do is find the transfer function between V sub G and V sub 0, the input to the output. The nice thing now to look at is if we simply look at what's happening at the non-inverting terminal, is there's no current flowing into that node or into that input location in our op-amp. And because of that, effectively, we can simply analyze this sub-circuit by itself. It's in isolation. All we really need to know is, let's find V sub P. If I know, so here's the thought process. Let me find a relationship between V sub G and V sub P. Once I have that relationship, I know V sub P and V sub N are the same. Can I find a relationship between V sub N and V sub O? And the answer is yes. If I simply do a KCL at the V sub N node, I can relate V sub N to V sub O. I already have a way of relating V sub G and V sub P. Now I simply need to realize that V sub P and V sub N are the same, and I can now relate V sub G to V sub O. That makes sense? Let's look at the first sub-circuit, which is, I'll just call that this one on the non-inverting terminal. And I'll just call it the V sub P sub-circuit. And we can do that because I sub P, the current going into that op-amp, is 0. So that now all we can need to worry about for starters is this circuit. Here's SL, and here's, hopefully I called that R sub 1. And this particular point was V sub P. And we can now say, oh, that's that voltage between that terminal and ground. That's the V sub P. Questions on that? And now we've worked this circuit to death. That's just a voltage divider again, circuit. Or if you wanted to, you could find the current and then find the product of the impedance SL times that current to find an expression for V sub P, if you feel more comfortable doing that. But from this, hopefully it's clear that V sub P of S is now SL over R1 plus SL times V sub G of S. And that's in neither time constant form or pole zero form. And if we wanted to, we could write it in one or the other. Suppose I now want to write it in time constant form. I can now factor the R1 out, and I have SL over, whoops, don't need an extra S in there. I factor the R1 out, and now I have this particular circuit. And let me, or I could have written it in pole zero form. If I factored the L out from the numerator and the denominator, I would have S over S plus R1 over L. Questions on that? That's now one transfer function between the input voltage and the non-inverting terminal of this op-amp circuit. And that now has, where is my zero located? At zero, at the origin. We'll call that the origin. Now I'd have a thumbtack right at the S equals 0 origin in the S-plane. And I have a finite pole at minus R1 over L. That 0 is now going to actually be coming up for all frequencies. That S is always on. It's never going to get turned off or on because there's no plus anything here. This S is always active. So as a frequency response picture, it's coming up from below, and then when this guy kicks in, it changes that slope by minus 20 dB per decade, while I was going up at plus 20 from that 0, and now I flatten out. So this transfer function, in effect, looks something like this, where this particular location is now the R1 over L. This slope is due to the 0, and we're coming up at 20 dB per decade, that 0 at the origin. So this is like a high-pass filter behavior and not a low-pass filter behavior. And this is just the first piece of the overall circuit. And that maybe is the more challenging piece, or what I was thinking might be the more interesting piece for your homework. So hopefully now you know how to find BP in terms of EG. What I haven't done is, in the book, this upper piece is a little bit more elaborate, but the ideas should be the same. So you might have something a little bit more going on in the feedback path, but you should be able to lump all of that into an impedance instead of a resistor and do the same kind of analysis. Let's now look at what's happening up at the top. Now we can analyze again this piece and say, well, let's just look at KCL at that inverting input node location at V sub n. Or we now say, because, well, let me not say that just yet. Let's say now KCL at the inverting terminal. We have Vn minus 0 over R sub 2. That was the current going to the left out of that V sub n. That's connected to ground. So we have V sub n to minus 0 over R sub 2. Plus, what's the current going up or to the right through R sub f? Did everybody hear that? We have the voltage drop from left to right being V sub n minus V naught, and now we divide that by the resistor, which is R sub f, and this is now our relationship at the inverting terminal of our system. We can now rewrite that a little bit. We can say 1 over R sub 2 plus 1 over R sub f, scale the V sub n, and that's equal to 1 over R sub f times V sub 0. I can rewrite that in terms of V naught by simply multiplying both sides by R sub f, and I end up with R sub f over R sub 2 plus 1 times V sub n. And I now, because of that upper piece in my overall circuit, I now have a gain associated with my device, the gain being 1 plus R sub f over R sub 2. And if those two resistors were equal, I would have a gain of 2 in that portion of my circuit. So that now I have the overall transfer function. If I called this transfer function, let me call this H sub n. And what if I called this H sub p for the P terminal and the N terminal? That's where those are coming from. Now I want to have the overall transfer function from the input, capital V sub g of s, all the way to the output, V sub 0 of s. But V sub p, remember, is the same as V sub n because of this negative feedback. That allows me now to say that this overall transfer function between V sub g and V sub 0 is H sub n times H sub p, which if I multiply all of those together, I end up with R sub f over R sub 2 plus 1 times s over s plus whatever H sub p was it R sub 1 over L. So in general, we have a situation like this. We just multiply the two transfer functions, or we do a functional combination, which in this case is multiplication. So the question was, how do we combine transfer functions, I believe, is the generic question. And in this particular case, we did have the fact that V sub p was equal to V sub n. But if it was some other relationship, we might have to do something other than multiply. But what we had is the following. So you can just sort of follow yourself along. You can say, okay, V sub 0 of s was this H sub n of s times V sub n of s. And now replace this with V sub P, which was actually H sub P of S, V sub G of S. And by doing that, I now can say that V sub 0 of S is equal to H sub N of S times this, which is H sub P of S, V sub G of S. You really just need to do whatever combination is specified by the way the circuit is configured to obtain your overall transfer function. But in this case, it was a cascade of transfer functions which produces a product of transfer functions. So in this case, the question was what actually happened in the overall transfer function, which I don't know what I want to call this. Was this about our fourth transfer function in terms of circuit? That overall, H sub 4 of S does differ from the first piece simply by that factor. So it's only a scaling of the magnitude. Our first piece looked like that. And so now we have this scaling behavior. And what's the DC gain of this overall transfer function? What's the DC gain of this transfer function? If I put in a constant to this circuit, if I said V sub G of T is a constant, what's V sub 0 of T going to be after it reaches a steady state? 0. That inductor is going to short, and you can see analytically that if you replaced S with 0 in this particular representation, you get 0 out. And if you looked at this, this is just like what we had before. It's just that now our values might have changed a little bit, but whoops, the structure of our frequency response looks the same. And it's going to break at the same location. Let's now talk about combining. That's now some ways of finding the transfer function, H of S, capital H of S. And if you wanted to, if you needed to do convolution, you could inverse Laplace transform those capital H's into lowercase h of t's to find the impulse functions. You now could then convolve waveforms to find your output response, or if you wanted to, you could multiply their transforms to get the response of these particular systems. In the time domain, suppose we go back to our first circuit. Whoops. And we'll just call this then the passive low-pass filter. What was its impulse response? We didn't derive it, did we? We had the transfer function. What was our transfer function for this guy? So if this is our S domain, was this 1 over RC over S plus 1 over RC? Is that what we had? That's our transfer function for this passive low-pass filter. What's our impulse response? We have a scaling factor of 1 over RC, and then this single pole gives us something like that. Let's look at a particular example. Suppose that we just said, oh, let's let it be let's say that our time constant was 1/10 of a second. If RC is 0.1, then we get this 10 e to the minus 10t as our impulse response for that low-pass filter. And we can hopefully see that graphically. Whoops. Let me make it sharper. So that this is now this 10 e to the minus 10t. What if we, and what does that look like then in terms of the pole zero diagram if we now slide up and realize that this right side of my hypothetical page is now the S-plane or S-domain. What do we know about this transfer function h sub 1 of s in the S-plane? If we wanted to sketch the pole zero diagram, what would it look like? How many open circles or zeros would I put on that S-plane? None. And I have a pole in the example that I used at minus 10. That was my pole location. That's my system. Let's now apply a particular input waveform or signal to that. Suppose now that my input is, let's say, x of t equal to e to the minus 2t. As a time domain waveform, this should be something that you can visually see or appreciate. This is just a decaying exponential. And that blue line looks like an e to the minus 2t. What's the time constant for this input waveform? Pardon? The time constant. So the settling time might be 5 time constants, but in this case, the time constant itself is the value of time where the exponent becomes 1, and that's 1/2. Now we take 5 of those, and it gives us a settling time of 2.5 seconds. So if I was sketching this very accurately, after 2.5 seconds, my blue line would be almost on top of my green line. It'd be 1%. Or at 0.01, and I can't sketch that accurately anyway, so I'm basically on top of 0. Now, what does this look like in the S domain? I now have one pole at minus 2. Now, if I wanted the response, I now need to combine. If I wanted the response of this passive low-pass filter, if I now excite it with an exponential decay, you now know how to find the total response in the new terminology that we've been using. In the past, you would simply connect up a voltage source of e to the minus 2t to that low-pass filter and derive the output response, V0. Now we have it in terms of transfer functions and inputs. If we now wanted the output, we could derive it in the time domain. And I would suggest that you better be able to convolve x with this decaying exponential and that h, another decaying exponential, to find the answer, y of t. Another way to find it would be to do it into the frequency domain. So now you jump across that crossed dashed line, and you say, well, I know what that is, y of s, and you could actually even sketch the S-plane plot. What colors was I? So I had my input signal being represented by that blue color. My system pole was over here at -10. And what is y of s? That's the product of my system transfer function, h of s, with the signal's Laplace transform, capital X of s. What was h of s? Wasn't it 10 over s plus 10? And the input waveform, 1 over s plus 2. And now you know how to inverse Laplace transform to find the complete solution, y of t, little y of t. You now know if you did this, you're going to have the structure that looks something like that. And I hope if I did the numbers right, I end up with 10 over 8. And actually, let me go ahead and put my minus sign here. I have 1 1/4 over s plus 2 minus 1 1/4 over s plus 10, if I did the partial fraction expansion correctly. So that y of t now, from this solution approach, if I now simply do the inverse Laplace transform, this will now be 10 over 8, which is 5/4, or 1 1/4, e to the minus 2t minus e to the minus 10t u of t. And that's what you should get if you went the other way and did the convolution. You should be able to get the same answer. And how you play with that depends on what you need or how you want to go about attacking that problem. Now that was for a particular input waveform, which was a decaying exponential. What if the input is a cosine omega naught t? Let's just think about this in the frequency domain. What's this picture going to look like? Our system hasn't changed, has it? We're still using this low-pass filter with a time constant of 1/10 of a second. So we now have this transfer function of our low-pass filter being 10 over s plus 10. That hasn't changed. So that gives us this pole. And you can see that I don't put the gain in here. I don't have a way of putting the gain in here, the 10 over s plus 10. You just have to remember that if you're sketching things or drawing things. But you can put the poles and the zeros. And the poles and zeros are important because the poles give us our structure of the result, our output response. Now, if x of t is a cosine waveform in the time domain, what does that look like in the s-plane? If you Laplace transformed this x, what do you have? You have that, don't you? S over s squared plus omega naught squared with the gain a associated with it. Where are the poles? Those are plus and minus j omega naught, meaning I now have, if this is j omega naught, I have a pole there, and I have another pole at minus j omega naught, and I actually have, for this cosine waveform a 0 at the origin. That's now my pole 0 diagram for y of s, capital Y of s. Can you see the structure of your little y of t based on those poles? This piece is due to the input, and this piece is due to the system, but the combination of those two give us our output signal. And what do we know about those two poles on the imaginary axis? What do they have any decay associated with them? Is there an e to the minus something t? There is, it's just that something is 0, right? E to the 0 t. So there is no damping associated with those. There's right on the imaginary axis. So now I'm shaking that filter at omega naught. And that corresponds to this. Now, what kind of a y of t are you going to see? You'll have a decaying exponential piece due to that minus 10, and you'll also have a sinusoidal steady state piece due to those poles at the origin, or on the imaginary axis. And that's jumping out at you based on this pole 0 diagram. And if you wanted to, you could say, well, my y of s is now h of s, x of s is 10s over s plus 10 s squared plus omega naught squared. What if I changed it up a little bit and I said, okay, that's well and good, and you could inverse Laplace transform that, but it's not too difficult. But you now know that you will have a sinusoidal steady state answer. What if I changed it a little bit and said, okay, here's your input. Now I've shifted where my t equals 0 point is. I now have a phase shift. The gain is still the same, capital A. The frequency is still the same, omega naught. So now I've shifted the time t equals 0, and what might that have done to my answer for y of t? Now effectively I have sines and cosines at omega naught is one way of thinking of it. Or you now have, again, a shifted version of your cosine waveform. Let's now see if we can, without finding the complete solution, the total solution, can we use the transfer function, capital H of s, together with this input signal information to determine what's going to happen in the steady state, in the sinusoidal steady state, and directly find what's going to happen. And we know already what's going to happen. If I shake this at omega naught, you know that the output is going to be moving at the same frequency, omega naught. It's just the amplitude might be different from A, and it may be shifted in time, so it may have a different angle. And what we want to do is figure out how we use H, the filter or the transfer function, to give us that information. This is all because of time. This is all in a section of the book, 13.7, but this is using the transfer function, h of s, to obtain the sinusoidal steady state output response. Section 7 of chapter 13. So let's see if we can quickly do this. But the punchline is the following. What you're going to do is if you have h of s, you will evaluate that at whatever frequency you need to find the response at. And that will give you now h of j omega naught. And that could be a complex number. But any complex number that you have, you can find its magnitude and phase, or magnitude and angle. And that's how the magnitude will be adjusted, and that's how the angle will be adjusted, or the phase shift in your argument of the cosine. So this will now have an and if I called that angle theta, then if I put in x of t equal to a cosine omega naught t plus phi, then the output in the sinusoidal steady state is going to be a, but it's going to be adjusted by the magnitude of h at omega naught cosine omega naught t plus phi plus this theta. So that's what we want to show, but that's shown in section 7. So if you can now find your transfer function of this system or filter h of s, and you now shake it at a given frequency, if omega naught was 2, you would evaluate that at h of j2, and you can do that. You can just replace s with j2. That gives you a magnitude and an angle. That now tells you how your amplitude of your input x of t is adjusted, either squished or expanded, depending on what h of j2 ends up being. And it tells you how your angle or argument in the cosine waveform is changed by an angle of theta. So let's look at this. We now have x of t as our input. And in general, that's some amplitude at a frequency omega naught and some angle, phi. And that's our time domain. In the phasor form, this is now A at an angle of phi. What is the Laplace of x of t? We can find that if we simply remember what the cosine of a plus b is. Just use the sum of angles formula for the cosine, and then we will end up with a cosine omega naught t and a sine omega naught t, and I'm saying, or I'm assuming that we know how to Laplace transform those pieces. Meaning, if we rewrite this, x of t can be rewritten as a times the cosine of omega naught t cosine of phi minus a sine omega naught t sine of phi. And what we will do is then we will simply collect this a cosine of phi piece. That's just a number, cosine omega naught t, minus a sine phi sine omega naught t. Now we can transform that. We have s over s squared plus omega naught squared times this coefficient. And we have a sine phi times omega naught over s squared plus omega naught squared. And those are both over the same denominator. That's now our input transform. And if we want the sinusoidal steady state, we could find the complete solution by hitting our system H of S with this input X of S and then inverse Laplace transform. But all we don't want the total solution, we just want the sinusoidal steady state solution. Which I am labeling little y sub SS of t, which is our sinusoidal steady state output response. And we want to find that if somebody gives us the system's transfer function h of s and the sinusoidal input x of t. If we wanted the Laplace transform of the complete output response, that would just be h times x, where those are capital. And if x is this structure that we just said, if x of t is this a cosine omega naught t plus phi, then we know that y is h of s times this a cosine phi s minus a sine phi omega naught all over s squared plus omega naught squared. In order for this sinusoidal steady state to even make sense, we need our system to be stable. If our system was not stable and we started shaking it, what's going to happen? You'd start smelling something burning, or it would blow up, right? If you had an unstable system and you excite it, it's going to go unstable. So in order for this to even make sense, let's assume that we have a stable system or transfer function. If we have a stable system, then if I shake it, then the output will be a stable response, and it will just have an adjusted amplitude and a changed phase. That's the assumption that we're going to make. Suppose h of s is associated with a stable system, that is, or i.e., all the poles of this system, h of s, are where? They're in the LHP, if you need to text this tonight, right? They're in the LHP, the left half plane. And if they are in the left half plane, you can now think of this complete response, y of s, as being made up of two pieces. One is the sinusoidal steady state piece, and the other piece is the transient piece, which is due to all of those poles of h of s that are in the left half plane. Remember the S picture, the S domain picture? Your h of s now has all its x's in the left half plane. And your x of t now has sprinkled 2 poles on the imaginary axis. You want to know what are my residues of those 2 poles at plus j omega naught and minus j omega naught. If you can find those, then you can find your answer. And that's effectively what we will do to find this. We can now rewrite this as this piece will give me a K1 over an S minus J omega naught plus a K1 star over S plus J omega naught. Those are the 2 pieces, plus I have these pieces that are due to the terms due to the stable poles of h of s. And if we can find K1, then we're done. We can now find the sinusoidal steady state answer. We may pick up at that point, but you have this material in section 7 of the textbook. And I'll see you then on Thursday.